In part 2 of this series, I'll show you two more examples on how to find the eigenvalues of a matrix. Now in part 1, we looked at question number 1, and here we had a 3 by 3 matrix. In this video, I'll show you how to tackle matrices that are in lower triangular form. That's when you have these upper zeros and all the numbers are situated at the bottom left corner. And I'll show you an example where the eigenvalues happen to be complex numbers. Let's continue with question number 2. So it turns out that when your matrix is in a lower triangular form, as is the case here, the eigenvalues, the ones represented by the Greek letter lambda, happen to be the numbers on the main diagonal. So our eigenvalues are 5, -2, 8, and -1. Now of course you can prove this on your own, and if your matrix happens to be in upper triangular form where the numbers are at the top and you have these zeros at the bottom, it's the same thing. The eigenvalues are on the main diagonal. In question number 3, we have to find the eigenvalues for the matrix A, and we'll use the formula, the same formula that we used in question number 1, right here, where we will take this matrix, subtract it by a scalar lambda times its identity. So -1, -2, 1, 1. This matrix minus the scalar lambda, which is what we're looking for, and the identity of this will be 1, 1, 0, and 0. And the resultant matrix, we will take the determinant of that, which we will set equal to 0 and find the eigenvalues. Anyway, after subtracting these two, you should end up with -1 minus lambda, -2, 1, and 1 minus lambda. So that's one element, that's another, and that's another. And just to show the difference, our matrix is 2 by 2, and these are its elements. We can find the determinant of this using the shortcut method for 2 by 2 matrices, and that's when you take the product of this diagonal and subtract it by the product of this diagonal. So the product of this and this is -1 minus lambda times 1 minus lambda minus the product of these two, which is -2, so it's simply +2, and that's equal to 0. Let's go ahead and multiply this out. So expanding here, we end up with -1 plus lambda, negative lambda, plus lambda squared, plus 2. And these two terms cancel out, leaving us with an incomplete quadratic lambda squared plus 1 is equal to 0. Solving for lambda, we get two solutions, of course. We'll have lambda squared is equal to -1, and square rooting both sides, we get lambda is equal to the square root of -1. Now you can't square root a negative number, otherwise you'll get an imaginary number. And in this case, we will get an imaginary number, which is simply I. So it'll be plus minus I. So in case you end up with an imaginary number, eigenvalues can be complex numbers, as is the case here. And there you have it. Two more examples on how to find the eigenvalues of a matrix. And if you have any questions, make sure to leave a comment below.